Hi there. As promised, I am here to do a few more sector area problems for you. Let's start with a quick review of what we talked about in our previous video, and that was how to find the area of a sector of a circle. And we discussed that that was a percentage of the total circle times the area formula. And then we did a fairly simplistic example. I'm going to move through the remaining problems in this section in this video. Let's start with example 2. Again, this is a fairly straightforward problem. It's good practice. First thing I'm going to do is label my radius because a lot of the information I need is already in my circle. For this one, I'm not given the central angle, but I can remember that a central angle and its intercepted arc are congruent. So this central angle is actually 20 degrees also. That gives me everything I need to find the area of this sector. I'm going to start by writing my formula because that's just the way I roll. And we're finding area, so this is going to use the area formula. I have recently, as in like the last few seconds, figured out what my central angle is. I'm going to write that as 20 degrees over 360 times pi radius squared, and in this case my radius is 3 squared, and I am good to go. What I need to do first is simplify the fraction 20 over 36, which is really 2 over 36, and that simplifies to 1/18. And then I'm going to multiply that times pi times 9. Yes, pi times 9, and I know that 1/18 of 9, or 9 over 18, is really just 1/2. So this ends up being 1/2 pi. So not a hard calculation. We knocked it out in no time flat. The arc length, we have not calculated yet. We'll do that in a moment. The sector area we calculated as being 1/2 pi units squared. And I'm not going to lie, when I looked at this, I thought it was just asking me for the measure of the arc LM, but I think it's actually asking me for the arc length. I can calculate that. Let's see, arc length. It's a pretty simple calculation as well, except that this time I'm going to use the circumference formula, which is 2 pi r. We already know that our central angle is 20 divided by our 360. Just going to go ahead and substitute information in, and our radius was 3. This simplifies to 1 over 18. 2 times 3 is 6 pi, and 6 over 18 is 1/3 pi. So that is the arc length measure. And I know that this is a linear unit, a linear measure, so it's just units. You could also write this as pi over 3 or pi over 2. Those are equivalent forms. They both work. Okay, example 3 is a little bit different. We like mixing things up. I notice in this circle that I'm given the radius, which is pretty groovy. But instead of being given the central angle or even the intercepted arc, I'm actually given the area of this sector. And I'm asked to find, actually that's not area, this is, I can tell because it's not units squared, this is the arc length. So I'm going to put this over here. This is my arc length is equal to 8 pi. So in this problem, we're going to have to work backwards. I'm going to start with my arc length formula. The arc length formula is central angle over 360 times my circumference, 2 pi r. I'm going to go ahead and substitute in what I know. In this case, I know the arc length. So I'm going to put my 8 pi over here. I do not know my central angle. That is actually the thing we are searching for. I'm going to multiply that by 2 pi. I do have the radius, we said that was 18. 16, I can read. Oh, look at me. Okay, and now I'm gonna do some simplification. Guys, that's all of the geometry involved. We wrote out we've written the representation of this circle in a geometric formula. The rest is gonna be some algebra. And there are different ways to solve this algebraically. You can choose the method that works best for you. I'm gonna kind of do it a long way. I'm gonna show you more explicit steps. If your brain does it a different way that's more efficient, more power to you. The first thing I'm gonna do is I'm going to simplify this expression with x over 360 times 32 pi. And that is still going to be equal to 8 pi. I'm going to simplify this one more time. And that actually simplifies to 8 over 90. So I'll draw myself a little arrow. And this becomes 8 pi on the left. And over here, I've got 8 pi over 90. To get rid of that denominator, because y'all seem to not like fractions, I'm going to multiply both sides of my equation times 90, because 90 divided by 90 simplifies to a 1. 8 times 90 actually comes out to 720 pi, but now that's going to be equal to 8 pi. And if I simplify one more time, where's my x? I forgot my x. Don't lose your x. Okay, so I'm trying to get x by itself. That's why it's important I don't lose it. I need to get rid of the 8 pi. That way my variable will be isolated. So I am going to divide both sides of this equation by 8 pi. And when I do that, the pi's simplify. This obviously simplifies. 720 divided by 8 is 90. So my central angle in this case is 90. And you might have thought you could just guess that by looking at this picture, but remember, we never assume. In this case, our angle is 90 degrees. And we've proven it algebraically. We're going to try the same tactic with example 4. This time, we are given the area, and it tells me, if I actually read the problem, it tells me that I have been given the area. We're going to work backwards as we have done in the previous problem. And I'm going to start by writing out my formula. Again, it's a percent of the whole circle, that's a 60, times the area formula pi r squared. In this case, we know the answer. The answer, if you want to think of it that way, or we know the area, is 432 pi units. And that is going to be equal to my central angle, 120 divided by 360 times pi. And here's what we don't know, guys. We're trying to find the radius. So I'm just going to leave that as a variable. That is the geometric representation of the problem that we have been given. Simplifying and solving for r becomes an algebra problem at this point. First thing I'm going to do is simplify 120 divided by 360. I'm going to leave the left-hand side of my equation alone. This comes out to 1/3 pi radius squared. From here, I am going to get rid of this 1/3 using the same strategy we did before, and I'm going to multiply both sides of the equation by the number 3, because 1/3 of 3 simplifies to just 1. And over here, I end up with a really big number. 1296 pi is equal to pi r squared. I'm going to get rid of that pi symbol by dividing both sides of my equation by pi. Those simplify out, and I end up with 1296 is equal to my radius squared. And lastly, when I take the square root of both of those sides, conveniently, it is a perfect square, and I end up with a radius of 6 units. And it's a linear measure because the radius is just a straight line. Okay, shall we do one more? Let's plow ahead. Example 5 is actually a lot like example 2. After doing the 2 previous problems where we were working backwards, in this one, we're just going to plow straight ahead. The first thing I'll notice is that I was given a radius of 10. I'm going to label my picture. My intercepted arc is the same as my central angle. And in this problem, I'm being asked for both the arc length and the sector area. I'm going to start by using the arc length formula, which again is a percentage of my circle times the circumference, 2 pi r. I'm going to substitute in what I already know, 120 divided by 360. You see that we've used that measure several times because it's free to use, and my radius is 10. From here, I do some algebra. This is all of the geometry involved. The rest is my algebra. 120 divided by 360, we know, is 1/3 times 2 times 10, 20 pi. And in this particular case, folks, I cannot simplify that any further. So I'm going to write this as a fraction because we know that that is the most exact answer I can give. And I'm going to say that this is a linear unit, a linear measure, so it's just units. Define sector area. I'm going to follow the same strategy. Area of my sector is going to be equal to a percentage of my circle times the area formula. I'm going to substitute in what I know. I know the central angle, part of the whole circle, pi, and we know our radius is 10, and I'm going to square that. This simplifies to 1/3, and 10 squared simplifies to 100. And again, I can't simplify 100 over 3 any further. Fractions are the most precise of our measures, so I'm going to leave this as a fraction and call it 100 over 3 pi units squared. And now we've done some extra examples, and I hope you understand how to work with sector area and arc length a little better.